let's learn about our first solution to viscous flows. We're going to learn about Poiseuille flow, which is an exact solution to steady incompressible flows. As we've seen previously, our viscous stress tensor for incompressible flow with a constant diffusion coefficient, it takes this sort of form. 1 over rho divergence of pi ij. This is equal to mu over rho times the Laplacian of our velocity, which is also equal to the kinematic coefficient of viscosity times the Laplacian of our velocity. We know that because of the character of Laplacians, that if we get to a small enough length scale, viscosity will matter more or less no matter what this coefficient is, even if this coefficient is quite small, so long as it's non-zero. So viscous flow could be very, very important for small passages that flow is going through, or pipes. And that, in fact, is what motivated Poiseuille to study Poiseuille flow. Poiseuille was a doctor. Poiseuille was interested in a particular viscous flow through a particular set of pipes. Poiseuille was interested in the viscous flow of blood through veins in the human body. We'll see that Poiseuille flow is a pressure-driven flow, and this was a model for how blood moves through the veins pumped by the pressure coming from the heart. So let's see what Poiseuille flow looks like. So let's start with our momentum equation with viscosity included. So we're d by dt of u plus our nonlinear terms u dot grad u plus our gradient of pressure over rho, and this is equal to our new del squared u, where this we recall is mu over rho, and all of this is from the minus 1 over rho times the divergence of our viscous stress tensor pi ij for this whole thing here, including the new coefficient. Okay, so let's start. So we said we want to consider steady flow. So we're going to make this first term 0. Let's actually be a little fancy here. Let's use a little purple here and make this 0. This is 0 because we're steady. And that leaves the rest of this. And before we actually go solving this, I'm going to solve it by drawing you a picture. I'm going to draw you the exact nonlinear solution to Poiseuille flow for steady flow, and I'm going to do it. I'm going to do it here for our pipe. So here's the walls of our pipe. I'm gonna draw our exact solution here. We'll come back and see how we know that this is the exact solution. But let's just draw what it is. Well, we know a couple things. We know that there's pressure. I'm going to have a high pressure at one end of my pipe. I'm going to have a low pressure at the other end of my pipe. So there's a grad P. There's a minus grad P that points in this direction, going from high to low. So that's the sense of our grad P over rho force being exerted here by, for example, the heart pumping the blood. And let's draw our velocity in purple. Well, what do I know? So I know that I'm going to have no velocity right at the walls. I'm going to have more velocity as I get away from the walls, and this is a characteristic of character of viscous flow near boundaries. And I know that the shape of this is going to be like this. It's going to be curved, and it's going to be a parabola with max at mid-channel. I know it's going to be 0, 0 at the walls. We would call this a no slip wall boundary condition. And this is the full, exact, in fact, non-linear solution. And that's quite a thing. Nonlinear solutions to fluid dynamics are hard to come by. So how do we know we can get the full exact nonlinear solution to this system? And how do we go about doing that? Well, the reason we can get a full exact nonlinear solution to this system is that the nonlinearities have a very special property to them in that they have no influence on the flow. They actually disappear from the momentum equation. So to recall, we're talking about our nonlinear term here, u dot grad u. It vanishes uniquely from the momentum equation. I'm going to show you why. So let's note some things. First of all, let's give ourselves some coordinates here. We're going to have an x coordinate this way. We're going to have a y coordinate cross channel this way. So x goes down the channel, y goes across the channel. So I want to make a couple of observations. All the flow is down channel. So all the flow is in the x hat direction. All variation of flow is in the y direction, is y hat. Okay, so if we write out our right, what that really is to say is that u vector equals u in the x hat as a function of y alone. So this is our full velocity vector is what these words are saying, and this actually has this has complete power. This is the unique thing about Poiseuille flow here. So let's consider our terms u dot grad operating on u, and let's write this out in all of its full glory in Cartesian coordinates. So this is u on d by dx plus v d by dy plus w d by dz on our u vector. Well, we know that that there's no w, there's no vertical flows. We also know that there's no, so W is actually in and out of the plane. V, this is our cross-channel flow. There's no V, so that term's 0. And we stipulated that there's no variation in the down-channel direction, that all the variation is cross-channel. So these are 0, and in fact, what this means is that u dotted with grad is 0. There's no alignment between the one place where we have gradients and the one place that we have flows. Okay, so what that means is that for any speed of flow in this simple laminar flow system, u dot grad u is 0, not because of anything about the amplitudes of u, but because of the geometry of the problem. By geometry, so this is true for all values, all amplitude values of u, and this is a quite powerful statement. All right, now let's apply this, and let's write down our remaining equation, our momentum equation. So we've got the gradient of p over rho, and I can also write this, by the way, for an incompressible flow. I can pull this rho inside here, I can even write this as a reduced pressure, pomega, as we'll do sometimes. So this is equal to our viscosity times the Laplacian of u. Okay. Or maybe more aptly, I can invert this if P is being externally imposed. So like pressure in a pipe under a pump. So if grad P is external forcing, I can actually invert this. So if grad P is known, if it's just some quantity, my pump can pump this hard, my heart can pump this hard, then I can write this problem as this, as the Laplacian of my velocity u. This is equal to dividing across our viscosity times grad P over rho. And remember, this is just a number, something that we know, and this is a number. This is some property of the fluid, right? Different fluids, different viscosities, different pumps, different grad P's, different fluids, different rhos. Nothing complicated here. This is also, by the way, just for sort of cleanliness of notation, this is also grad P over mu, with mu being rho times nu, which is our relationship between dynamic and kinematic viscosities. So given this, the first thing I want to observe is the following. We can now actually solve u as the double antiderivative, so we invert the Laplacian operator on grad P over mu. And so we can solve and invert this problem. And this is all just a constant. And so we know that u, if u is in the, this is a constant in the x hat direction, the direction of our pressure. We know that u then is equal to something, some function of, well, we know it's going to be a function of y squared and y and of constants times the x hat direction. And then we can use our boundary conditions. We can note that u is 0 on the walls. That's our no slip boundary condition, which is the typical boundary condition for horizontal flows next in a viscid fluid. And that gives us very quickly the coefficients in front of y and y squared and constants, and we get that u is parabolic in shape. And 0 at the walls, which is how I could draw the exact nonlinear solution by just drawing my walls and then drawing a parabola in between my walls and then filling my parabola up with the appropriate velocity vectors for my flow, and I knew that I had my exact nonlinear solution to Poiseuille flow. Okay. There's a couple things that Poiseuille flow is incredibly powerful for. So on the one hand, Poiseuille flow can give you flow in a pipe. On the other hand, Poiseuille flow can give us a handle on viscosity. So this will be part 2. So for part 2, since we have that grad squared of u is equal to grad p over mu from our momentum equation, then we actually have a way to, we could either use this to solve for u, or if we instead know u and we know grad p, then in some sense, we can invert for mu. We can solve for mu. And we get that mu is given by grad of p over our Laplacian of u. And since this is laminar flow, this ends up being well posed. And what we're really talking about is we're talking about some sort of integral over the pipe or tube, and then we'll be normalizing by the cross-sectional area of the pipe to get. So if we integrate over our pipe area, this is the definition of a weighted average for our mu. And this gives us a mu that's the average viscosity of our fluid. And this is one of the ways that the dynamic viscosity mu can be measured simply by pushing fluid through a pipe and seeing the rate at what you do is you apply a pressure. You measure the mu. You measure the mass flux. You measure u amplitude, and that gives you the viscosity of your fluid. And that's a simple empirical way to determine the viscosity of fluids with simple lab tools.